At the beginning of the spring 2014 semester, our group was presented with the task to create working 3D printers with the help of a pre-existing 3D printer. These printers were to be created for student and faculty use at the West Texas A&M Department of Engineering. Our group members consisted of Yvette Bravo, Doug Todd, Craig Carlton, Cameron Bevington, and Juan Ramirez. 3D printing designs can be made up from up to 80% of printed parts. Our design statement tasked us to create a 3D printer using another 3D printer to replicate the parts. In order to do this, with the help of the engineering department, the MakerBot Replicator desktop printer was purchased. To expand our understanding of 3D printers, the group decided on two different designs to build for the university: the Rostock Delta 3D printer and the InventorBot 3D printer. The idea of 3D printing is not a new technology. It actually dates back to the mid-1980s. However, only within the past 10 years have 3D printers begun to increase in popularity and have become more available to the public. As supporting technology has become available, designs for 3D printers have become much more in-depth, efficient, and effective. 3D printers are now devices that are easily accessible to the public for everyday use. It is predicted that 3D printers will eventually be household items much like the PC to create everyday objects instead of buying them from the store. This revolutionary technology has the ability to facilitate the design, modeling, and fabrication of future and existing designs.
3D printing works by first converting a three-dimensional CAD drawing into a series of thin, separate layers. When the print begins, the hot end heats up to melt the plastic filament being driven into it. Next, the printer starts to print each layer of the drawing. In this picture, you can clearly see the layers, which are about 0.4 millimeters thick. As mentioned before, the MakerBot Replicator was chosen to serve as the primary printer and was used to print the necessary parts for this project.
Before the building began, the group set out to focus on meeting a few requirements. Cost effectiveness was very important. A fully assembled 3D printer can range from $3,000 and up. We wanted not only to make the printers affordable in order to be able to replicate in the future, but we also wanted to make the printers cost affordable to maintain. To help the maintainability of the printers, we also decided to provide the department with user-friendly manuals. We also wanted to make the printers as safe as possible. The printers were going to be used by faculty and students. Therefore, we wanted to make sure to be able to tuck away any hazardous wires or hardware within the frame of the printers. Since the printers were going to be used by faculty and students, we also needed them to be aesthetically pleasing, easy to use, and easy to maintain. In order to meet the requirements mentioned, these two models were chosen for the build: the InventorBot, which will be used as an in-class printer, and a version of the Delta 3D printer, which can be used both as an in-class printer and a portable printer. We will be discussing what makes these two printers unique, but first, let's understand the general makeup of 3D printers. We came to find out that 3D printers consist of 5 major parts: the frame, the XYZ axis, the extruder and hot end, the building platform, the electronics, and the printing software, which is open source and available online. One of the things we found interesting was the differences that both models had to offer. These differences included the printing coordinates, the material of the frame, the printing surface, and the printing speed.
One of the biggest differences that you will see between the two models that were built is the printing axis. The InventorBot prints in an XYZ Cartesian coordinate axis, moving the extruder in the X direction, the platform base in the Y direction, and the build platform in the Z direction. The modified structure of the InventorBot that we made is extremely aesthetically pleasing. The rigid frame provided made it perfect for an in-class use printer. Although there were extensive amounts of components, the assembly was moderately simple and the overall cost was much lower than the Delta. It was noticed that the steel frame actually eliminates 40% of the parts and therefore reducing cost. In the case of the Delta printer, the software translates those X, Y, and Z coordinates into polar coordinates. The arms of the printer move in a more circular fashion. This actually gives the printer an advantage on printing speed, making it 1.4 times faster than the Cartesian coordinates. The frame of the Delta printer was built with birchwood. Birchwood was chosen because it is light and does not experience as much warping as other woods. The Delta printer built allows for the ability to print taller objects on top of a hotbed. This hotbed gives the base of the prints a more polished and glossy look. This printer also had a very low cost.
One of the major obstacles we came across in this project was to understand the build and the software that was necessary to keep these printers running. The printing technology is relatively new to the public and it was completely new to the group. Therefore, learning the build from scratch was intensive. A detailed build was provided in the user's manual in case another build is desired. The software was another necessary component that needed to be tackled. The open software used needed countless modifications in order for the printers to work properly. A detailed description of the software modifications was also provided in the user manuals. The group also set out to improve the quality of the prints being printed. Without good quality prints, the printer becomes less valuable. In order to be able to improve the quality of the prints, we set out to experiment with hot end nozzle sizes in order to maximize printing speed and the quality. We found that the 0.5 mm nozzle maximized the printing speed but didn't sacrifice the quality. We also found that the hotbed gave the base of the prints a more polished and glossy look and allowed the filament to grip the surface better than painter's tape. Experimenting with the repetier settings gave us the printing quality that we were looking for. Detailed descriptions of repetier settings are provided in the user manuals.
The revolutionary design of these 3D printers is broadly dependent on open source ideas. Since both of the motherboards were Arduino based, the Arduino Integrated Development Environment, or IDE, was used to update the firmware to the boards. This environment is written in Java and based on processing, AVR-GCC, and other open source software. Within the Arduino IDE, certain open source firmware can be loaded and then modified uniquely to any printer. Marlin and Sprinter firmware were used for the Delta and InventorBot respectively. Any computer-assisted design or CAD program can be used as long as the drawing is exported into an STL file, also known as Standard Tessellation Language. The STL files are widely used for rapid prototyping and computer-aided manufacturing. NetFab is a common software used to check and repair STL files. This is an important step because if the STL file has any defects on the surface geometry, then the project will not print properly. The idea of open source technology allowed us to use a variety of software, and through trial and error, Repetier Host was finally used as an actual printing software. Repetier Host utilizes the slicer program to take a final 3D model and recreate it by converting it to G-code, or X and Y, Z coordinates, to define it in space, layer by layer.
Finding the optimal printing quality required countless hours of experimentation. The picture above shows a few test samples that were printed in order with the first prints of the Delta 3D printer on the left. As can be seen, the quality drastically improved and was found to be primarily dependent upon three different settings: the feed rate, the hot end temperature, and the hotbed temperature. The printer is now printing at its optimal performance. The feed rate chosen is at 300 millimeters per second, the hot end temperature at 220 degrees Celsius, and the hotbed temperature at 70 degrees Celsius.
We did have a big delay in the arrival of the MakerBot printer, which didn't arrive till March 31st, and further part shortages and delays were caused by the jamming of the MakerBot after just 1 week of usage. However, the overall outcome of the printing quality of the printers built was above satisfactory for the time allowed in this project. The group was ultimately able to provide the West Texas A&M University Department of Engineering, 2 functional printers that are easy to use, maintainable, cost-effective, and aesthetically pleasing at a very low cost. The Delta at around $520 and the InventorBot at $409. It is also very important to keep in mind that all details needed to run printer and printing software can be located in the user manuals provided. As engineers, the development and experience that was gained from this project changed the way we looked at prototyping and building new designs. Each member of the group believes 3D printing technology will only get bigger and will help bring future and existing projects to life. We would like to give a big thanks to the Department of Engineering for the purchasing of the MakerBot printer that allowed this project to succeed, and to Dr. Hunt for her support and allowing us to work on this project.